Hello. 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 Am I audible?
Yes.
Okay. Good evening, all. I am Saurabh and I welcome all of you to this live session for the NPTEL course Applied Computational Fluid Dynamics. Someone is trying to join, but I don't know. Okay. So this is our first session. And in this session, we will try to solve some problems which are based on the content of week 1. Okay. And I hope that this session will be helpful for you in solving your assignment problems. And if you have any doubt regarding anything which is related to content of week 1, then you can ask. Okay. Should we start or we should wait for a few more minutes?
Let's wait for 1 or 2 minutes.
Okay. Okay, till then we can have a brief introduction. I am Saurabh and I am from IIT Kanpur. I am doing my doctoral research in the Department of Mechanical Engineering. You can also introduce yourself. Mukund. We have Mukund, Niranjan, Omkar, and someone named U23ME023, Vaishnavi and Vishal. So Apur,
Yes, sir.
you are UG student or MTech or PhD?
Yes, sir. UG.
Okay, you are from?
I'm from Bihar, sir.
Okay, no, I mean your institute.
Yeah, I passed out from PhD track Coimbatore.
Okay. So anyone else want to introduce, then he or she is welcome. Or I think we can start now. So you might have gone through the course content and you can see that this is a very broad course. Starting from very basics, it covers most of the concepts which are required for solving any problem using computational fluid dynamics. Okay, like uh, in first few weeks, we discuss some concepts related to fluid dynamics, thermodynamics, governing equations. Then how do we discretize? How do we do meshing, boundary conditions? And then we discuss something related to turbulence modeling. And at last, we also cover LES and DNS, right? Large GD simulation and direct numerical simulations. Okay, so since this is a very broad course, so some concepts may not be discussed very thoroughly. So if you have any doubt, then I request all of you please discuss here and also go through any good textbook, okay, for your basic concepts, right, which are prerequisite for this course. Okay, so in week 1, we have discussed some basic reviews of fluid dynamics and thermodynamics, right? So before starting, I will just try to briefly summarize. So course is computational fluid dynamics, right? So as the name suggests, computational fluid dynamics, right? So you are trying to solve some problems related to fluid dynamics using some computational techniques, right? So computational techniques which we use in CFD, they are different from our, you know, regular techniques, which we call analytical techniques, right? For example, if you solve some differential equation, you can get exact solutions, right? So there are some analytical methods you can get the general solution of many differential equations. But governing equations of fluid dynamics, they are very challenging, right? And most of the time they are not possible to solve uh, analytically. Okay. And we don't know that whether the general solution of these governing equations exists or not, right? So what are the governing equations? They are called Navier-Stokes equations. They are second order non-linear partial differential equations, and we don't know the solutions, the general solutions, and we also don't know whether the general solution exists or not, right? If you can answer this question, then you will be like, this is called this is one of the millennium problem, right? This is one of the great unsolved problem till now. Okay, so if you can solve this problem, then you can get 1 million prize, by the way. Uh, Governing equations are really difficult. Non-linear partial differential equations, second order. So we use some computational method. Okay. So what these computational methods do, they do some sort of discretization, and this discretization basically converts these partial differential equations into some algebraic equations, a lot of algebraic equations. Okay. And these lot of algebraic equations are solved using computers. Okay, so that's what we do in computational fluid dynamics. We are trying to solve some fluid dynamics related problem using some computational techniques. So one very important thing before starting any CFD course is, first of all, you should understand this FD, fluid dynamics, right? So what are the governing equations, what you are trying to solve, right? You have any problem, and then you model that problem, and you get some sort of equations. So first step is to know what you are trying to solve and why you are trying to solve, right? Until unless you know what you are trying to solve, then you will go for how to solve, right? So first you should understand what you are trying to solve. Okay, so in first few weeks we will try to go through these equations, okay, fluid dynamics, and something related to thermodynamics, because this thermodynamics will be required for compressible flows. Okay. So these are the steps in any CFD, right? So first we do pre-processing. So what we do in pre-processing, we create a geometry. So creating a geometry is something like defining our computational domain, right? For example, fluid will come from, for example, you have a pipe, and in pipe there is some flow, and then you define, okay, from this side flow will come, and from that side flow will go out, that is outlet, and this is our boundary, this flow, there will be no slip condition. Okay, so like that you define the geometry. Then you discretize your geometry, that is called mesh generation. Then you also define material properties. What are the materials involved? Materials are your fluid, and sometimes maybe your uh, solid, right? For example, you have wing of an aeroplane. Then of course that will come under some solid mechanics problem, but you also need to define fluid properties, right? Viscosity, maybe surface tension, or density, or any other fluid property. You also need to define boundary condition, right? If you don't have any boundary condition, you cannot tell the solution of a differential equation. You solve the differential equation and you check that whether the solution of differential equation is satisfying the boundary conditions or not. Then the solvers, what solver do, as we have already discussed, it uses some computational technique to solve the equations, the governing equations. So what are the governing equations of a fluid mechanics problem? That is mass conservation, momentum conservation. Uh, we can go for energy conservation, and if you are trying to solve some other things related to maybe electrohydrodynamics, then you can also go to Maxwell equations. Okay, equation of state, and any equation, right? Any equation that is related to your fluid flow problem. Okay, using some computational technique. Now most of the systems are very, very complex, and there is not a single phenomena that is going on. There are a lot of phenomena that are going on. Okay. But if you try to solve all of those phenomena simultaneously, then it will be really, really difficult. Okay. Then what we do modeling. In modeling, what we do, we check what are the uh, important things that we want to see. Okay. What are the things which we want to analyze, right? You don't want to analyze everything, right? So there are some models. Models are basically equations. Okay. They are simply can be written in some mathematical forms. Okay. They are models. For example, turbulence modeling. You know, turbulence is again one of the unsolved problem, right? Many times people, you might have heard this quote that quantum physics and turbulence, these are two things, main things which had not been understood properly yet, right? So turbulence, as you know, this is very, very difficult to get the general solution. So again, there are some models, simple models, sometimes complex models. Combustion, you know, combustion, internal combustion engines, your gas turbine, your any engine, right? There are combustion going on. So what is combustion? Combustion is basically a chemical reaction. So what is a chemical reaction? In chemical reaction, what you have? You have a molecule. That molecule breaks down into atoms, some radicals. Those radicals combine together and they form the product. Okay. And heat is being released or maybe consumed. Okay. So there are a lot of radicals. Even very simple equation, a very simple reaction. For example, combustion of methane. The combustion of methane itself will produce many radicals, right? Hydrogen radical, oxygen radical, water, many intermediate radicals. So all these things can be written in terms of mathematical equations. Okay. So this whole process is called the modeling. So same thing goes for heat transfer, radiation, any other process, right? So there are models. Models are basically equations of physics, right? For example, if you want to model a particle which is experience some force, that model, you know, F is equal to ma, very simple model. So similarly, there are model for everything. Okay. Then we put the initial conditions, right? We do some sort of monitoring that whether we are going in correct direction or we need to tweak some parameters. Okay. So all these things, these equations and these settings, models, they are put in a solver. That can be your a commercial software like Converge or ANSYS or Cosmol Multiphysics or any sort of solver, or you can write your own solver. Okay. Then you will get the results. Okay. Those results may be the velocity field or the temperature or pressure field that you do post processing. So post processing is basically your decoration, some decoration, not decoration, I mean the plotting, contours, graphs, right? So post processing is basically the step in which you can visually inspect the results, right? Okay. So these are the main processes that you do in a CFD. Okay. So again, the important part is, the most important part is, I think this one, this one, this one, all of these are important. But before starting, you should understand what are the governing equations, what are the physical models, and the solver settings. Okay. So now you have a basic idea what we do in CFD. Now we can start our discussion. Okay. So in the first week, we have also discussed something related to compressible, not flows, but compressibility. That is, you can say thermodynamics, right? So now we will try to solve some problems. Okay. If you have any doubt till now, then please ask. If you don't have any doubt, then we will try to solve some problems. And these problems are similar to your assignment problems, right? So Prasad is asking something. Yeah, please.
Can you brief about convergence model? A short explanation
Okay.
on the previous slide.
Convergence criteria.
Please.
Okay.
Yeah.
So in convergence criteria, what you should see, you see something called residue. Okay. So residue is the difference between the true value and the computed value, right? So you see that with each step, whether this residue is decreasing or it is not decreasing. So what you want? You want the residue to decrease. Okay. So residue is like some sort of error, you can say. or the difference between the computed value and the actual value. Okay, so this will be discussed in upcoming lectures, but you can understand this thing as uh, the difference between the true value and the computed value, or you can visualize this thing as a residue, and you want this residue to be decreasing with more and more iterations. Okay, so there are some iterations. Okay, probably I forgot to discuss. Iterations are basically in one step you don't get the solution. Okay, so in one step you get some solution, then those solutions are fed into another iteration, then you another get some solution, then another again you use that solution of the previous step to the for the next step. So step by steps, iteration by iterations, there are a lot of iterations. So with each iteration, uh, with iterations going on, we want this residue to decrease. Okay, and the value should converge to a value, right? For example, velocity, for example, let us assume you already know the answer, and answer is 30 meter per second. Okay, you want the velocity at a point, and you already know that it should be equal to 30 meter per second. In the first iteration, let us say you got the value like 25 meter per second. In another iterations, you are getting 28, then 29, then 29.5, then 29.75. So you can say that it is converging towards a value, right? So that is what we mean by convergence. But sometimes it may happen that your mesh is not very good, or your model is not, your discretization is not very good. So what can happen sometimes? First step, in the first iteration, you're getting 25, then 100 meter per second, then maybe 200 meter per second, then again maybe 10 meter per second. So there can be fluctuations, fluctuating values, or it can be, a non-converging, right? So convergence means it is going towards a value. Okay, in with each step you are approaching towards 30 meter per second. Okay, so that is what we mean by convergence, and this convergence can be monitored using the residue. Okay, so in the first step, for example, you are getting 25. So 30 minus 5, sorry, 30 minus 25 is equal to 5. That is your residue. In another step, you are getting 28, then 2 is residue. Then you are getting 29, then 1 is residue. Then 29.5 is the residue. So this residue should, residual value should decrease, and your velocity value or any parameter value that should converge towards a value. Okay, so that is what we mean by convergence, and that is monitored using residuals. Okay.
Yes, clear. Thank you.
Okay, thank you. Now there are some problems, and these problems are similar to your, I think, assignment 1. Okay. So the question 1, first question says, so question number 1 says the speed of sound in a purely incompressible flow is. I think you can easily answer this question. The relation of speed of sound with the compressibility, right? What is the relation? Hello?
A square is dou p by dou rho.
You are saying a square is equal to dp by
dp by dou rho,
right?
and isentropic.
Yes, isentropic. So yeah, this is correct. And this thing, dp by d rho, or at least d rho by dp, right?
0.
0? No. Okay, before solving it using mathematics, just use your common sense. What will happen? You have studied the speed of sound, or maybe speed of waves in a medium, right? You have let us say a string or wire that is some tension, and you you do calculate the speed of wave in that in that medium? You remember? Hello? You know your guitar. Let us say you have a guitar string and it has some tension in it. Then there are some waves. What is the speed of wave? So it is dependent on this tension, right? So if this medium is very stiff, then the speed is more, right? Stiff mediums have more speed. Okay,
Yes, sir.
anyways. Okay, so this dp by sorry, d rho by dp, it is what? It is basically representing the change in density when you change the pressure. So it is related to your compressibility, right? If you just divide it by rho, then you get the compressibility. This is how you define the compressibility, right?
Yes.
So you can write compressibility as in terms of speed of sound as Ts is equal to 1 by rho a square, right? From these two equations, correct?
Sir, could I ask a question?
Yes, sure.
Sir, actually, the thing is, I joined just now because I'm outside. Is this meeting going to be
Okay.
recorded so that I can refer to this later on?
Yes, this meeting is being recorded and I will upload this on the YouTube. And I think you can get the
Okay.
link from your NPTEL platform.
Okay, sir. Okay. Thank you.
Okay.
Thank you so much.
Okay. Okay. So you can write Ts is equal to this, right? 1 by rho into a square. Very simple. So now if this Ts is equal to 0, if this Ts is equal to 0, then what will be A? A should tend to infinity, right? From this equation, you can write dp by d rho as 1 by Ts into rho, right? So A square is equal to 1 by Ts into rho, correct? Is this correct?
Yes, sir.
Because A square is equal to, already you have told that it is equal to dp by d rho at constant entropy, isentropically. So if Ts is equal to 0, then A should be infinity, correct? So correct option is third option,
Infinity.
right? So purely incompressible flow will have infinite speed of sound. Okay. So this is very important if you think a little bit more. So incompressible flows means the in sound speed of sound is infinite. And if you think about sound, what is sound? Sound is basically propagation. Sound is a wave, right? So sound you can model as a pressure wave. So if there is some disturbance in pressure at a point, that disturbance travel through the medium. That can be air or any fluid, right? And this disturbance travels at a speed of sound in that medium, right? So if the flow is completely incompressible, purely incompressible, that means the any disturbance made at any point that will be instantly be appeared at everywhere, right? So that will be traveled at infinite speed, right? So these small concepts will be helpful later, but I hope what I mean, right? So if there is any disturbance, that disturbance will travel at infinite speed, and that change will appear everywhere instantly, right? That will be appear instantaneously. Someone is joining. Okay. Okay. So I hope it is clear that in a purely incompressible flow, the speed of sound is infinite. Just remember these relations. Okay. Now coming to question number 2. Question number 2 says, which numerical method in computational fluid dynamics can approximate the derivative at ith point using any n number of points on either side?
Finite difference.
Finite difference, yes. If you have watched the lectures, then it is very easy, right? So if you use more points, that means you are using higher order scheme. So error will be less. So that is the benefit of using finite element. That we cannot use in finite volume, right? So this finite difference, finite volume, that has been discussed briefly in this lecture, and this will be discussed in detail in upcoming lectures. But for the time being, I hope it is clear, right? Finite element, sorry, finite difference, right? So in finite difference, you can use uh, n points to calculate the derivative at ith point. Okay, so what I mean is, for example, you have any curve and you want to calculate the derivative at this point. Let us say this is ith point. So at I minus 1th point and I plus 2 point. Okay. So using the values at these 2 points, you can calculate the value at this point. Okay. So what will be the derivative? Let us say it is x, and the distance, this is delta x, this is again delta x. So and this is, let us say it is v. Then dv by dx at point I, this will be equal to at plus 1 minus at minus 1 divided by 2 delta x, right? So here we are using 2 points, but you can use more points. Okay. So how do you do that? That will be discussed in detail in upcoming lectures. But that's what we mean by using ith at ith point, calculating derivative at ith point using n number of points on either side, on this side and at another side. Okay. So if there is no doubt, then we will move to the next question. Uh, you should know something related to Taylor series from your mathematics. So if you have not studied, then I will request you to kindly go through the Taylor series expansion. Okay. Okay. Now coming to the question number 3, it says that in CFD, which approach can use a particle centric frame of reference? So this is your fluid dynamics, right? So there are many approaches like Eulerian approach and Lagrangian approach. So what is the difference between Eulerian approach and Lagrangian approach?
Eulerian is control volume approach, and Lagrangian is control must be trace individual particles in Lagrangian.
Yes,
Whereas
exactly. Yeah. So Lagrangian is your basically particle or control mass based approach, right? So you are tracking individual particles, right? So Lagrangian is your particle centric frame. Okay. And Eulerian, as you told, this is Cartesian.
Control volume.
Sorry, control volume. Control volume. And most of the time we want to solve our problem in control volume perspective, right? For example, you have, again, let us say a duct flow. The flow is going through the duct. So you're not tracking each and every particle of the fluid that is going through duct. You are observing what is going inside the duct, right? So there should be some method which can work as a bridge between control volume and control mass. And what we call that? What is that tool?
Reynolds transport theorem.
Reynolds transport theorem. Okay. So most of your equations or equations of physics, they are written in terms of a particle. For example, you have a particle of mass m, there is some force F, then you know F is equal to ma, or F is equal to dp by dt, rate of change of linear momentum. So this equation is written in terms of a particle, for a particle, but you want to focus on, again, a number of particles and for a given volume. Then the simple looking equation that takes the form of Navier equation, Navier-Stokes equation. Okay. So, anyways, so we will move to the question number 4. Question number 4 says the isentropic compressibility of air at 0.5 atm is. So there are 4 options. So these options, please excuse me, this is 10 to the power minus 5. First one is 10 to the power minus 1.41 into 10 to the power minus 5 meter square per Newton. Similarly, other options. Okay. So it is saying isentropic compressibility. So compressibility is compressibility, compressibility tells how much there is change in density when there is some change in pressure. Okay. But there is a suffix, isentropic compressibility. So there should be another type of compressibility as well, right? So if there is isentropic compressibility, so what is another compressibility?
Isothermal.
Isothermal. And both of these have been discussed in detail in the lecture. So for isothermal, what is the relation? What is the equation? Isothermal means temperature remains constant.
For air, it's 1 by P.
So isothermal here, temperature will be constant, 1 by V. Okay, so I am putting this this bar sign so that you don't confuse this V with the velocity. Okay, so this is a specific volume at constant temperature, and isentropic entropy will be constant. Okay. So this change, whether this takes place at constant temperature or at constant entropy, uh, that's how we define isentropic and isothermal compressibility. So for isothermal, tau is equal to 1 by P. Is this right? Hello? You can simply derive it, okay? You can simply derive it using ideal gas equation. So ideal gas equation, you know, PV is equal to RT, right? So V is your RT by P. Hello? So dV by dP at constant temperature, that will be equal to RT by P square and minus 1. So, minus RT by P square. Okay. So you just put this thing here. Okay. So what you will get? You will get TT is equal to minus 1 by V and then minus RT by P square. Okay. Then RT by P square or P times P. This RT is equal to PV. So that cancels out and you get 1 by P. Okay. So isothermal compressibility is the reciprocal of pressure. Okay. Similarly, you can derive it for isentropic. If you write it for isentropic, then it comes out to be Ts by gamma. Okay, gamma here is Cp by Cv. I am not driving it. It has already been discussed in the lecture. So I request you to kindly go through that. If you have any doubt, then I can discuss it here. Should we discuss it? Hello, is there any doubt in this formula?
No, sir.
No, sir.
Okay, it is discussed in the lecture and you can kindly go through that. Okay, so we have to find which compressibility, isentropic compressibility. So first we can calculate the isothermal compressibility and just divide by gamma. So gamma for air, it is approximately 1.4. Okay, gamma for air, it is approximately 1.4. And isothermal compressibility will be 1 by pressure. What is the pressure given? It is 0.5 atm, 0.5 atm atmospheric pressure. And in 1 atmospheric pressure, you know, it is approximately 1.013 times 10 to the power 5 pascals. So 0.5 into 1.013 into 10 to the power 5 pascals. Okay. This is your isothermal compressibility. And isentropic compressibility will be just divide this thing by gamma. Okay, so it will be 1 divided by 0.5 into 1.013 into 10 to the power minus 5 times gamma 1.4. Okay, so you can calculate this value. Let us calculate it. 1 divided by 0.5 times 1.013 times 10 to the 1.4 into 10 to the power not minus 5, it is plus 5, sorry. 10 to the power 5 pascals. 10 to the power 5 pascals. Okay, so it is coming how many zeros? 1, 2, 3, 4, 5. 1.4 into 10 to the power minus 5. Okay. So is there any option? Yes, first option is there. 1.41 into 10 to the power minus 5 meter square Newton. Okay. So option A is the correct option. So these equations are important. Okay. This will be used very frequently when we discuss compressible flows. Okay. Okay. So if is there any doubt, then please ask, or if there is no doubt, then we can move to the question number 5. Okay, I think there is no doubt, and we can move ahead. Question number 5 says the specific gas constant for methane is. So what is specific gas constant?
Universal gas constant by molecular mass.
Yes. So specific gas constant R is equal to universal gas constant RU divided by molar mass, right? Correct? So universal gas constant, you know the value. What is the value? 8.314, right? Joule mole Kelvin, right? Joule per mole Kelvin. And molar mass of methane is how much? Carbon is 12 and plus 4 hydrogen, approximately 16. Okay, sorry. Uh, 16. So how much it is? It is coming 0.519625. Okay, joule per kg Kelvin. Okay, sorry, here it was kilojoule per.
It will be gram, sir. Joule per
Huh?
gram Kelvin.
Oh,
Sir, it will
sorry.
be joule per gram Kelvin.
Okay, hello, that's what you are saying.
Yes, sir.
So if you write in kilojoule Kelvin, then sorry, kilogram Kelvin, then 519 point something, right? Correct.
Yes, sir.
So which option? Option A, B, C. Third, sorry, last option, fourth option. Correct. Okay. I hope this is clear. Then if there is no doubt, then we can move to question number 6. Question number 6 says, how can convergence of a CFD solution can be accessed? How can convergence of a CFD solution can be assessed? Okay. How do the assessment of convergence of a CFD solution? We have discussed when we were discussing this diagram. Someone asked about this convergence. So by convergence, what we mean that values of any parameter of or any quantity that should converge to a value. Okay. For example, if you know that correct value is 30 meter per second, then in the first iteration, if you get like 25, then second iteration you get 28, then 29, then 29.5, then 29.75, like that. If it is going, then most probably it is converging. Okay, it is going towards a correct value. So what is happening here in the first iteration, the value you are getting is 25, and the difference with the true value is 5. In another step, you are getting 28 and difference is 2. In third step, difference is 1. And next step difference is 0.5. Then in the next step, difference is 0.25. So this difference is continuously decreasing. Okay, the difference that imbalance, okay, that error, that is continuously decreasing. So that's how you track whether this solution is converging or not. Okay. So that's what we mean by convergence. So there are 4 options. First option, by tracking the imbalance, also known as residuals. Yes. Option B says the number of iterations. Third option says the complexity of geometry, or 4 options says by the type of fluid used. So these third option and fourth option does not make any sense, right? By type of fluid, it should not affect the convergence, right? The complexity of geometry, it can take more iterations. Okay, it can converge slowly, but the complexity does not tell does not tell whether the solution is converging or not. Okay, so with each iteration, it is converging or not, that we can track from this residual, okay, or the difference or the error, okay, the imbalance. Okay. So there are some methods in which a solution will converge fast. There are some methods where solution will converge slowly. So it is, if it is converging fast, then the solution, the number of iterations will be less and the computational time will be less. Okay. If there are more iterations required, then it will take more time. So what you want the problem to be solved in less steps. So you want the solutions to converge fast. Okay. So this convergence criteria can also be a criteria to judge a algorithm or a computational model, which one to use. Okay. So you will definitely will try to use that one in which the convergence is fast. Okay. So if there is any doubt, then you can please ask, or we can move ahead. Okay. Now coming to the question number 7. Question number 7 says, which factor strongly influences the accuracy of a CFD solution? 4 options again. The type of mesh, spatial discretization, right? This is your computational domain, and you discretize it, and what you get is the mesh. Second option says the order of accuracy of a numerical model. Third option says the number of cells in the mesh, and last option says all of the above. So the type of maze, the first option, you know there are many types of maze: structured maze, unstructured maze, right? And how small these cells are, okay? If these cells are not small enough to capture small scale structures, then there will be many things which you cannot analyze. Okay, for example, if there is a eddy, okay, there is an eddy, and your maze is bigger than this eddy, then in this maze you will get only one velocity vector, right? Only one velocity vector. You will not be able to resolve this eddy, right? If your maze is bigger than this eddy. Okay. So you know that in flows, especially high speed at high Reynolds number, there can be eddies of very small size. Okay. And if your maze size is not small enough to capture these eddies, then you will not get the correct option, correct solution. Okay. Then there are some models. Okay. And the type of maze, you know, structured maze and unstructured maze. The structured maze usually will give you the better results. Unstructured maze will are not that good as compared to structured maze. But you know, in most of the engineering problem, the geometry is quite complex and it is almost impossible to get the structured maze every time. Okay, you will have to go for unstructured maze, at least at the boundaries, right? Inside the domain you can get the structured maze, but at some points you will have to go for unstructured maze. Okay, so the type of maze, this does influence the accuracy of the CFD model. Then the order of accuracy of the numerical model. Yes, if you are using uh, higher order accurate numerical model method, then definitely it will give you accurate results within the given number of iterations. Okay, for example, if you want to do the simulation for, let us say, 10 iterations or 20 iterations, let us say 20 iterations, and you have two models, one is a higher order accurate and another one is not that higher order accurate, then higher order accurate will give more accurate results in the given number of iterations. Okay, so the solutions will converge fast. Third option says the number of cells in the maze. So yes, there is something related to this thing that I discussed just a few seconds ago. If there is very few cells, then you will say, okay, the maze is coarse maze. It is not fine maze. Okay. If there is number of high number of cells, then we say it is finer maze. Okay, if these cell size is smaller. But if you increase the number of cells, then it will take more time, right? Basically, you are solving more equations. Okay, so you have to do a trade-off between the number of cells and your computational time. Okay, so in engineering, you don't want exactly the exact answer. Okay, you want the answer which is accurate enough to give you the values within a limit. Okay, you are not solving these equations analytically, so always there will be some error, and that error should be within the acceptable limit. Okay, so basically all of these influence the accuracy of CFD solution, the type of maze as well as the accuracy of numerical model, the number of cells. Okay, so when you do a CFD analysis, you should keep all these things in mind. Okay, the type of maze, which type of maze you are using, which type of method you are using, and how many cells are there. And uh, as we discussed that if there are more cells, it will take more time. So at some places you can make the cell size bigger. At some places you will have to make the cell size really smaller, right? For example, there can be some locations where there are these small eddies and you want to resolve these. So in those areas, you will have to make these the cell size smaller. Okay. In another area, you can increase the number of increase the size of the cell. Okay. So that's how you make a mesh. Okay. There are a lot of other factors that we will discuss maybe in upcoming lectures. Okay. Okay. So question number 8, it says, what is the purpose of post processing in CFD? So we discussed there are 3 steps mainly. One is pre-processing. In pre-processing, we do define the geometry, we discretize, we make the mesh, we tell the initial conditions, we tell the fluid properties or material properties, right? Then there is solver. Okay, within solver, we apply some models. Okay, and we tell the governing equations. Okay, we do track the convergence. Okay, and other things. And finally, when you get the results, then we do post processing. So in post processing, what we do? We do some sort of plotting, contour plotting, or graph making like that. Okay. So that is post processing. So what is the purpose of post processing? You have already solved a problem. You have already got the values. Then why are you doing post processing? Option A says to optimize the geometry. Answer is no, because you have made the geometry in the first step itself. That is the pre-processing, right? Second option says to visualize and analyze the results. So yes, it is the correct option, right? You have the results, you want to analyze these visually, okay, by making some graphs or plots, okay, and then you can analyze, okay. You have some idea uh, before you get the results, okay. You have some prior idea, okay. So this type of results I am expecting. So if that matches your, intuition or, physical reality, then you can say it is, we are getting correct results, right? And third option says to verify the initial conditions. Again, no, it is not correct, because the initial conditions we give in the first step itself, in the pre-processing itself step. Also joining. Okay. To define the grid convergence criteria, no. We do post processing after getting the results to visualize and analyze the results. Okay, so second option should be the correct one. Okay. So if there is any doubt, then please ask. If there
Sir,
is
what
no
do we
doubt,
mean
then
by grid convergence? Hello,
Huh?
am I audible, sir?
yes, yes.
Sir, what do we mean by this grid convergence criteria?
Okay. So as we discussed previously, that your results will depend on the size of the these cells in the grid. Okay, right? So if you make these cells very big, then also you will get some results. Okay, that those results may not be accurate. Okay, there can be small structure it is that cannot be captured by these bigger cells. So what you do, you make this cell size smaller. Okay, you make this cell size smaller. Then again you get the results. Okay, then you expect there's that since we have made these grid cells smaller, now we should get accurate results, right? Here you are getting some in the bigger one you are getting some other results, smaller one you will get some other results. Then again if you reduce the size of these cells, again the results should change. But if this result is continuously changing as you are decreasing the size, then there's some problem. Okay, at some point your results should not depend on the grid, right? So like you have many grids. Okay, so if you keep on decreasing the size of these cells and your results are keep on changing, then you will be confused which one to use. Okay, so at one point you will reach you will reach a point, you will reach to such a maze which has small enough cells that your results will no longer change. Okay, even if you reduce the size of these grid cells, the change in the results will not be that much. Okay.
Okay, sir.
Then again, if you reduce the cell size, what will happen? The change in result will be negligible, but the change in time will be more, right? Here there are 1, 2, 3, 4, 9 cells. In the second one, you have more cells. In the third one, you have even more cells. So as you are increasing the number of cells, you are reducing the size of cells. The time will be increasing, right? It will take more time because the number of equations are being increased. For each maze, for each cell, you are solving some equations. If you are increasing the number of cells, you will have to solve more equations, right? So if you solve more equations, it will take more time. So if you decrease the cell size, then definitely you expect that there will be some change in result, and you will expect more accurate results. But at some point, even on reducing the cell size, the result will not change much. Okay, so then we will say, okay, now results are converging with respect to the grid size. Okay, so that is very important. When you do a CFD analysis, you will have to show that your results are grid independence. Okay, that is something called grid independence test. Okay, so whenever you're doing these analysis, you take not just one maze, you take many maze with the reducing size of the cells. Then you will select that one for which your results are accurate enough. Okay, there is not much change, right? So basically, you are doing a trade-off between the time and the accuracy. So the result should the result should converge with the cell size. So that's what we mean by this. Okay. So there is something called grid independence test. So this grid independence test you should do whenever you are doing a CFD analysis, right? Now is that clear? Hello?
Yes, sir. Yes, sir. Clear, sir.
Okay. So now can I move ahead, or if there is any problem, then please ask. Now question number 9. It says, which of the following statement is correct regarding calorically and thermally perfect gases? This has been discussed in the lecture. The perfect gas or ideal gas is one which follow the ideal gas equation, right? So there are few assumptions for the ideal gas. One is that the particle to particle interactions are not there. Okay, so particles or the gas molecules, they are not interacting among themselves. Another thing is that they are very small, they have zero size. Okay, so they do not occupy any space. Okay, they are very small. Okay, and all the collisions that are taking place between these molecules, they are perfectly elastic. Okay, so that is our ideal gas. So for ideal gas, first of all, particles don't interact among themselves. So how can particles interact? Particles can interact chemically. Okay, so there are, let us say, there is oxygen molecule, there is carbon atom. Then there can be interaction. If there is enough temperature, then there can be combustion and they can interact to form carbon dioxide. So that is chemical interaction. Even if there is not chemical reaction, they can interact among themselves by using some sort of attractive force or repulsive forces, right? So whenever you bring two molecules near to each other, there will be some forces, okay, in the real condition, in the real scenario. But in ideal gas, we assume that intermolecular forces are neglected and gas is not chemically reacting. So that is our ideal gas, and ideal gas should follow the actually it do follow the ideal gas equation. But since you know that particles do have a finite size and they do interact among themselves, so that ideal gas equation need to be modified, and that modified equation is called van der Waal equation. There are a lot of other equations as well, but the van der Waal equation is most widely used. Okay. So perfect. There are two terms: calorically perfect and thermally perfect. So are they same or different?
Different, sir.
Different. So calorically perfect means that their internal energy is only dependent on temperature. Okay. Internal energy is only a function of temperature. And thermally perfect means their specific heat, that is you know
The calorically perfect, the specific heat is constant, and thermally perfect, the specific heat is function of temperatures.
can you please repeat?
The calorically perfect gas, the specific heat is constant, but in
Yes.
thermally perfect gas, the specific heat is a function of temperature. It varies with temperature, especially at high temperatures.
Yes. And why it happens? Because there are some other degrees of freedom which can get activated at higher temperatures, right?
Yes, sir. Ionization, dissociation, all that.
So degrees of freedom. For example, you have one molecule which has two atoms, and these atoms are bonded like this. Then usually at lower temperatures, this vibrational mode, for example, that will not be activated. Okay. But at higher temperature, some other degrees of freedom, they can be activated. Okay. So if higher modes are activated, then those modes will also take up some energy, right? They will also consume some energy. So a specific heat will change with temperature, right? So at higher temperature, more modes will be activated, and your specific heat that will be function of temperature. Okay. So calorically means the specific heat is constant. The specific heat is constant. That means internal energy is only function of temperature, right? And thermally perfect means this C is the function of temperature. Okay. So now you can answer this question. There are again 4 options. Option A, both calorically and thermally perfect gases obey the ideal gas law. Yes, both are perfect gases, then they should follow the ideal gas law. But only calorically perfect gases have constant specific heat capacities. So that's correct. That's what we have discussed just now. Second option says calorically perfect gases are a subset of thermally perfect gases, as both obey the ideal gas law and have constant specific heat capacities. So this is not correct, because thermally perfect gases, they don't have constant specific heat capacities at higher temperatures, right? At higher temperatures, the specific heat is the function of temperature of the thermally perfect gas. Third option says the thermally perfect gases are a subset of calorically perfect gases. So this is not correct, right? Because calorically perfect gases have the constant specific heat, and thermally perfect gases don't have the constant specific heat. Fourth option says both calorically and thermally perfect gases have variable specific heat capacities, but only calorically gases have obey the ideal gas law. No, this is not correct. Right? So which option is the correct one? First option is the correct option, right? Perfect gas, ideal gas, this should obey ideal gas law. Calorically perfect gas, constant specific heat, and thermally perfect gas, specific heat is the function of temperature only, right? Okay, and both of these follow the ideal gas law. Okay, it is just a definition based question. I don't think there should be any problem. So I think we can move to the next question. Question number 10. For which type of gas is the van der Waals gas law applicable? Calorically perfect gas, thermally perfect gas, real gas, none of the above. So van der Waals gas law, as we discussed, it is for real gases, right? Calorically perfect gas and thermally perfect gas, they follow the ideal gas law. And for real gases, the ideal gas law, it is modified, and the modified version is van der Waals gas law. Okay, but this van der Waals gas law can also be applied for ideal gas, right?
Yes, sir. The constants are taken 0.
Yes, those constants you can make in such a way that it is same as the real gas. Sorry, ideal gas. But since we have to select only one option, then probably third option will be the best one. Okay, but you can select these two as well.
Sir, in
Okay.
most
Please.
Sir, in normally the solvers that are available. So in
Mhm.
that solvers, which assumption that we take that the real gas or the calorific or thermal, like for
Most of the
NCs?
it depends which type of analysis you are doing. For example, I work in the field of combustion. So in combustion, I don't use ideal gas. Okay, I use some other models because combustion happens at very higher temperature, and as we discussed that at high temperatures, other modes are activated, and we cannot use the ideal gas. Okay, so it depends on your case. For example, if you are just analyzing the fluid flow, okay, fluid flow in a, let us say, in a pipe, and the temperatures and the speeds are not very high, and your flow is incompressible, then you don't need to solve any thermodynamic equation, right? You don't need to solve that. You just use you will only solve the momentum equation, only Navier-Stokes equation, right?
Yes.
So you can solve that I mean state equation as well simultaneously, but again that will increase the number of equation, okay, and it will take more time to solve that, right? So it depends what is your purpose, what are your conditions at which your phenomena is taking place. Okay, so for combustion like purposes we have to use uh, modified equations, and there are not only just van der Waals gas equation, there are other equations as well. Okay, more complex equations. Okay, so that's what it is. That's what is used in software solvers.
So in combustion problem also, this variation of specific heat will be there because of high
Yes,
temperature.
yeah, sure, definitely. At higher temperatures, the specific heats are more,
Yes.
right? That's why combustion processes are very complex. Why? Because there are a lot of species. Okay, for example, let us say combustion of diesel. So diesel itself is not a compound. Diesel is a mixture of many compounds, right? There can be heptane, hexane, decane, lot of compounds. Each compound has its own physical and chemical properties. And when the combustion takes place, each species will undergo different types of reaction mechanism. Lot of radicals will be formed. And when those radicals are present, uh, then they have again different properties. So number of equations is increased, you know, in a crazy way. Okay, lot of equations have to be solved. Okay, and at higher temperatures, again, you cannot use the ideal gas equation. And this specific heat is the function of temperature. Okay, at higher temperature, uh, specific heat is higher. Okay.
So, sir, while we are modeling combustion, so we have to solve mass equation, momentum, three momentum equation, energy equation, and other equation related to species.
Yes,
So we
yes,
have
exactly.
as we have the many number of species we have that many number of equations.
Yes, exactly,
Okay.
exactly. And number of species itself is not a constant. There is a whole, reaction mechanism. For example, you have methane, then in the combustion of methane, there will be some reaction mechanism. Okay, and again, this reaction mechanism itself is a model. Okay, you cannot note down all the species. Okay, the possibilities are endless. Okay, you have, for example, oxygen, nitrogen, uh, other gases can be present in the air. Carbon is there, hydrogen is there, so they can interact in many ways. Okay, there can be CH radical, OH radicals, and H2O can be there. C radical, I mean oxygen radical only. OH radicals can be there. A lot of other intermediate products are formed. So generally, usually what we think, what comes in our mind, that methane is reacting with the air. So carbon dioxide will be formed and water will be formed. So three, four things are there. Three, four things are not there. Okay, there are intermediary steps, and in intermediary steps there are a lot of species. Okay, the number of cases are really large. Okay. For example, something called oxides of nitrogen, NOx.
Yes.
So how this NOx is being formed? So there is a mechanism called Zeldovich mechanism. Okay, so you don't want NOx to form. For example, if you see the methane, you are combusting the methane, then what will you think? That methane is burning, so carbon dioxide will be formed, water will be formed. And if there is not incomplete, there is incomplete combustion, then carbon monoxide can be there. So like that we think, right? But nitrogen, uh, oxides of nitrogens are also formed. Okay, and these oxides of nitrogen, they are very harmful, right? You don't want NOx formation. Okay, so it is just off topic, but since you asked, then this NOx formation will take place at higher temperature. Why? Because nitrogen is N2, and this two nitrogen atoms are bonded by three triple bond, right? And oxygen is bonded by double bond. So oxygen molecule can be broken into atoms in the radicals at relatively lower temperature, but for nitrogen you have to break three bonds. So radicals of nitrogens are formed at higher temperature. Okay. So if your combustion is taking place at very higher temperature, then the nitrogen that is present in air, there approximately 80% nitrogen in the air. Okay. So those nitrogen radicals will also be formed, and they can react with the oxygen radical, and they can form the nitrogen oxide. So what you want? You want your combustion to take place at relatively lower temperature, so that uh, radicals of nitrogen are not formed. Okay. So that there is something called Zeldovich mechanism, and that tells that this NOx formation is higher at higher temperature. So you want to go for relatively lower temperature. There are other mechanisms using which you can reduce the NOx formation, but just an example I'm telling that when there is combustion, then there can be something which you can even forget to model. Okay, in between there can be some steps in which some really new things are coming. Okay, lot of species, and for each species there is conservation equation. For oxygen atoms, number of oxygen atoms should be conserved. For I mean, the number of atoms of each species should be conserved. Okay, so conservation equations are there. Specific heat is changing with temperature, so those equations. So a lot of coupled equations are there. Okay. Anyways, so I hope this is clear. Van der Waals gas equation is for real gases, and by setting the values of constant in a specific way, you can convert the van der Waals gas equation into ideal gas equation, and calorically perfect gas and thermally perfect gas both should follow the ideal gas equation. So all these three options should be correct. Okay. Is that clear?
Yes.
Okay, thank you. Moving to the next question, question number 11. Question number 11. What is a key reason for increasing use of CFD tools in the industry? Yes, CFD tools, the use of CFD tools is increasing in the industry. Okay. Four options. First option, reduced complexity of engineering designs. So this is very wrong option, right? Because the complexity is increasing, right? As the engineering is progressing, there are machines coming up which are very complex, right? The complexity is increasing. Okay. Second option, availability of simpler experimental methods. Okay, so if the simpler experimental methods are available, then we will like to go for those simpler experimental methods. Okay, but it is asking about increased use of CFD. So second option is also not correct, right? Third option says faster computing time and decreasing hardware costs. Yes, it is correct one, right? So like every year our processors are getting faster, right? The cost of hardware, it is decreasing. For example, 10 years ago, the memory cards that you are using, that can be like few gigabytes or hardly 1 GB, right? But now you are using like 1 in terabytes, right? So what I mean is that hardware cost is decreasing and computers are getting faster, right? The new chips, the new processors are coming. Okay, so that makes the CFD easy. Okay, the faster computing times and decreasing hardware cost. And the fourth option says limited capabilities of CFD software. So yes, CFD softwares have limited capabilities, but that is not the reason for increasing use of CFD tools in industry, right? Usually we consider experiments to be uh, better replicate the actual situation. Okay, if you want the more realistic results, then we try to go for experiments, right? Because in experiments you try to replicate the real situation, and in real situations then can be some phenomenon going on which you cannot model, or if you try to model then it is very difficult. For example, combustion, as we were discussing. Okay, you have an IC engine and you want to see the P theta diagram or the rise of pressure inside the combustion chamber with respect to temperature. If you go for simulation, okay, then sometimes you cannot write the equations for all the species. Okay, you try to cover most of the equations, most of the species, but there are you know many species, you cannot model all of them. Okay, so CFD will be very difficult there. But if you put a simple probe inside your combustion chamber, then you will get the exact pressure, right? Okay, so I hope this is clear, right? So, so do we move ahead? Question number 12. Okay, I think this is clear, right? Question number 12 says, which of the following numerical frameworks is most suitable for simulating flow over an aircraft with all control surfaces deployed? So flow over an aircraft with all surfaces deployed means the geometry is going to be very, very complex. Okay. And if you want to make a structured mesh, it is not possible, right? At some points, you will have to go for unstructured mesh, right? At least at boundaries. In that case, your finite volume method is best, right? This has been discussed in the lecture, and this finite difference, finite volume, spectral method, these will be discussed in more detail in upcoming lectures. But as you know that for unstructured mesh, for complex geometries, finite volume method works best, right? Okay. So moving to next question. Question number 13. Which of the following is not correct? First option says CFD typically provides higher resolution than experiments. Answer is yes. In experiments, there are limits on resolution, right? For example, if you want to visualize a flow, then what we use? We use high-speed cameras. And these high-speed cameras has limit on time resolution as well as space resolution, right? For example, cameras has some a megapixel, right? If it is 1 megapixel, that means there are 1024 by 1024 pixels. Okay. So it has some resolution, spatial resolution. You cannot go beyond that. You can use higher resolution cameras, even higher resolution cameras, but there will be some limit, right? But in CFD, you can keep on making, you can keep on make the mesh size small. Okay, definitely that will increase the computational time, but resolution definitely you can increase. Also, there is time resolution constraint in experiments, right? Each device has its highest sampling rate. You cannot go beyond that, right? For example, cameras, they can work at, for example, 4,000 frame per second, 10,000 frame per second. Okay, so there will be some limit. Okay, you cannot go beyond that. Okay, but in CFD, you can make your DT really, really small. Okay, you can keep on making this DT small. Okay, so you can get higher resolution, right? So CFD typically provides higher resolution than experiment. So this is correct. Second option says CFD typically provides higher accuracy than experiments. Okay, we will come back to this point. Third option says CFD generally less expensive than experiments. It depends on the situation. Sometimes CFD is more costly, sometimes experiments are most costly, but most of the time CFD is less expensive, right? It is like one-time investment. You have purchased the solver and server or processor, then you can do many simulations, CFD simulations. But for experiments, equipments are really expensive. Cameras, lasers, your probes, your actuators, they are very costly. Okay. Fourth option says the size of body is not a restriction for performing CFD. Yes, this is also true, right? For example, you have an aircraft and if you want to get the flow feel around the aircraft, you want to find that lift or drag, then you cannot put the whole aircraft inside a wind tunnel. Of course, you can make a smaller model. Okay, you can do a dimensional analysis. Okay, by making a smaller prototype, a smaller model. But size of the body is a constraint in experiments, right? But for CFD, you can make really big bodies, right? So option B is not correct, right? Typically, CFD typically provides higher accuracy than experiment. This is not correct. Experiments provide high accuracy. Why? Because experiments replicate the real situation better. Okay. So there can be some phenomenon which cannot be modeled and solved using CFD. Okay. As I gave you the example of combustion. Okay. When you are doing CFD, there will be some radicals which you cannot model. Okay. Or there can be some species for which model is not available. There can be some mechanism going on which you cannot model, or the mechanism is not available. Okay. So something can be left over. But the experiments, you just put a probe and you get the data. That is the accurate data, right? So experiments are typically more accurate because they replicate the real situation. Okay. So all the CFD models, whenever you are doing CFD, the CFD results first, they need to be validated against the experimental data. Okay. For example, you want to solve a problem, fluid flow problem, let us say, and you have a model, then you need to test that model on a problem for which the experimental data is available, and you compare the data. Okay. So that is called validation. So every time you are doing a CFD simulation, you need to validate your model with the experimental data, because experimental data is considered to be more accurate. Okay. So second option is correct too. Okay. Is there any doubt, or we should move ahead?
Sir, generally is not the experimental data considered as the benchmark? Generally, yes.
Experimental data is not considered as benchmark.
Means I want to say experiments are considered as benchmark, right?
Yes, experiments are considered benchmark. Okay, your CFD results, I mean, CFD models need to be validated against the experimental data.
So, you chose the second option. That's why I'm asking.
Second,
I mean, you chose the second option, right? CFD provides higher accuracy than experiments. So
that is the
generally,
correct option. Oh, sorry. We have to find which is not correct. Okay. Okay. Sorry. So we have to find which is not correct. So again, there is, it is a little debatable question. So since I'm an experimentalist, so I consider the experimental results to be more accurate.
generally we can't conclude, right, that CFD will
Yes.
provide higher accuracy than experiments.
Okay, so I leave this question up to you. Okay, you just select your own answer. If the problem is really simple to model, okay, then definitely CFD can be, more accurate, because experimental setup will have its own errors, right? Experimental errors, right?
Yes.
Each and every equipment, each and every probe you are using, that will have its own error. Okay. For example, you are measuring the temperature. Okay, you have a water, and you are providing some heat, and you are measuring the temperature. Okay, this is thermocouple. Then the data you are getting from experiment, that will depend, accuracy of that will depend on this thermocouple sensitivity. Okay, if this bead is very big enough, okay, if this bead is very big enough, then the temperature of bead, let us say it is the temperature of bead, and this is the temperature of water, they will not be equal. Okay, because bead will take some time to make its temperature equal to the temperature of water, right? If you put the bead suddenly into the water, it will not be suddenly equal to the temperature of water, right? It will take some time. So
Yes, sir.
that is kind of the time response of a equipment. Okay. So this is one example. Another example is like all these equipments, the working of these equipments that depend on the environment. So some equipments are really, really sensitive to the environment, to the moisture, to the temperature, right? So there can be some errors, but again, that will depend. What is your purpose? Okay. As I gave you the example of combustion, if you do the simulation of combustion, then the pressure that you are getting from the pressure transducer, that pressure transducer should be of very high quality. Then that data I will consider to be more accurate as compared to the CFD. Okay. So I will leave this question unanswered. Maybe we can discuss it more in some upcoming sessions. Okay. But the points should be clear, right? Why the resolution in the experiments cannot be infinite? Because there are some limits. Okay, your camera, for example, will have some resolution, some 1 megapixel, 2 megapixel, and it will have the limits on the temporal resolution. It can be 4,000 frame per second, 5,000 frame per second, but there will be some limit. Okay, and the experimental setups are usually more costly. Okay, and size is most of the time a constant in experiments. Okay, and the accuracy stuff that I will leave up to you. Okay. Now coming to the next question, question number 14. Which of the following is correct? Structured grids are common in industrial applications. Second option says unstructured grids provide more accuracy. Third option says a boundary layer grid is used to resolve the wake region. Fourth option says unstructured grids can be employed for complex configurations. I think there should be no debate in this question, right? This is very easy. First option says structured grids are common in industrial applications. This is not correct. Why? Because industrial applications, they are complex, right? In industrial applications, geometries are really complex. And when the geometries are complex, you cannot use structured grids everywhere, right? At some point, you will have to go for an unstructured, right? Second option says unstructured grids provide more accuracy. Again, this is not correct. Structured grids provide more accuracy, right? Third option says boundary layer grid is used to resolve wake region. Again, this is not correct. Boundary layer grid. Okay, in the boundary layer, the grid size is really, really small, and that is used to resolve the boundary layer region, not the wake region. Okay. Fourth option says unstructured grids can be employed for complex configuration. This is the correct option, right? Complex configurations will require unstructured grids, and industrial applications, they are mostly complex configurations, and for that we should go for unstructured grids. We'll have to go for unstructured mesh. Okay. So fourth option is the correct one. Okay. Now coming back to the moving to the next question. Question number 15. It says which of the following is correct? Solid and fluids have similar stress-strain relationship. Second option says solids have higher intermolecular distance. Third option says both liquid and gases are called fluids because they can flow. Fourth option says in solids, the force of attraction between particles is low. Again, very simple question. In solids and fluids, do they have similar stress-strain relationship? Answer is no. In solids, stress is proportional to strain, right? Stress is dependent on strain, right? If you assume that it is proportional, Hooke's law, then you can, write a linear equation. You can assume some relation between stress and strain. But in fluid, stress is dependent on strain rate. not on strain itself. Okay.
Yes, sir.
So in solids, stress, it is the function of strain, but in fluids, this stress is dependent on strain rate. Okay. So this is not correct. Second option says solids have higher intermolecular distance. So again, this is not correct, right? Solids have less intermolecular distance as compared to liquid, and gases have even higher intermolecular distance, right? Third option says both liquids and gases called fluid because they can flow. This is correct, right? Both of them can flow, so they are called fluid. So what is fluid? Fluid is something which can flow. Fourth option says in solids, the force of attraction between particles is low. So again, this is not correct. In solids, force of attraction between the particles is higher as compared to gases and liquids, both, right? So which option is correct? Second option is correct. Solids have higher intermolecular distance. Uh, both liquid and gases are called fluid because they can flow. Okay. So I think there is no debate in this question as well. Now, okay, so this was the last question. If you have any question, then please go ahead. Or if there is no doubt, then we will stop here. Is there any question or we should stop?
So I have a question, but it's not related to CFD. Not related particularly to this course.
Okay.
I wanted to ask you, since you are working on combustion, so what is the currently what is the hot topic in combustion? If someone wants to work in combustion.
Okay. So in combustion, there are many things. One is what you are combusting, right? So there are conventional fuels and there are some new fuels which are coming in the market, right? So conventional fuel were your diesel, gasoline, all these stuff. Now the non-conventional or renewable fuels are like methanol, ethanol, hydrogen, ammonia. Okay, so this is the fuel chemistry stuff. Another thing is the experiments. Okay, in combustion, now there is more focus on getting better results of simple problems so that we can develop better models, right? As we discussed that in CFD, the problem is that sometimes we don't have models, right? So if you have higher, better data, so you can validate the models. So that is another one. Okay. So for that purpose, a lot of new techniques are coming. The most of them are related to optics. Okay. Lasers, cameras. So every year there is some development and frame per second of cameras are increasing. The resolution of cameras are increasing. Okay. And another things that is like penetrating everywhere is like, machine learning and all. You have some data, people are trying to apply some machine learning models. Why? Because in combustion, there are a lot of degree of freedom, right? So you want to you want to reduce the number of variables, I can say, right? So people are doing reduced order modeling. Okay, so that is another one. And simulations are again, people are trying to develop new model, but again, that model will be required to be validated. Okay, so lot of aspects are there of combustion, like, so because combustion require knowledge of many fields, right? Chemistry you require physics. Sometimes you require the knowledge of CFD. Okay.
So any good online resources, if you can
Online
recommend?
resources for studying combustion,
Combustion.
experiment,
Combustion.
simulation, or just theory of combustion.
Yes, I think one will have to start with theory only first, right?
Yes, for theory, I think the good book is called S.R. Turn, right? Book by S.R. Turn, and there are some lectures. NPTEL lectures are also there. One is by D.P. Misra, I think from IIT Kanpur. There are two courses, course 1 and course 2 on combustion. There are a lot of other good courses on combustion as well. It depends, actually. I mean, there are a lot of topics. What is your focus? Okay, so on which topics you want to focus? The book SR Turn, I found it very well. Okay, most of the equations are explained very well.
I watched some videos. There was one French professor who visited IIT Kanpur. I think you would know, Thierry Punzo or something like that.
I think I'm not able to recall his name. Maybe I can try to search some good resources, and you can write to me and I can share. Okay, so you are working in combustion. Are you doing experiments or simulations?
No, sir. No, sir. I'm like I want to learn. I'm interested in that. So
Okay,
I was
you
thinking,
are you doing? I mean, which course you are doing? BTech, MTech, PhD, or you have done PhD?
no, sir, I passed out this year. Like I qualified grade also. I got good rank, but due to some personal reason, I could not join any institute.
You
So
have done
like
PhD, right?
no, sir. No, sir. I'm just a UG.
Okay. You
BTech.
you have done BTech.
Yes, sir. So like
Okay.
I gave grade. I got good rank also, but due to some personal reason, I could not take admission. I had offers. I had offers from good institutes, but due to some personal reason, I could not take admission. So what now I'm planning is to at least self-learn few things which I want to work in the future. That's why I asked you.
Okay. You can. I mean, mail me or you can text me. Okay. We can discuss it in
Okay,
the
sir.
direct message DM. Okay. So I think we should stop here. Maybe I can write my email here. SAURABHCH22 @iitk.ac.in. Okay.
Okay, sir.
So if I found any good resources, I will share. Okay. Okay. Thank you all for
Yes.
joining. We will meet in the next session. And if you have any queries, then we can discuss in the next session because time is, I think, over. Okay. Thank you all.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.